हेलो स्टूडेंट्स, एमएससी फाइनल पेपर 5 ऑर्गेनिक सिंथेसिस में हम लोग रिडक्शन के बारे में पढ़ रहे थे. इन दिस क्लास वी विल टॉक अबाउट रिडक्शन ऑफ एल्डिहाइड्स एंड कीटोन्स. द फर्स्ट मेथड दैट वी यूज फॉर रिडक्शन ऑफ एल्डिहाइड एंड कीटोन इज reduction by hydride transfer reagents. There are certain reagents like lithium aluminum hydride and sodium borohydride which are hydride transfer reagents, and they carry out reduction of compounds, and we use these compounds for reduction of carbonyl groups, aldehydes and ketones. The reduction of aldehyde to primary alcohols and ketones to secondary alcohol is easy to accomplish when we use these hydride transfer reagents. Lithium aluminum hydride is a powerful reagent, and this is commonly used in ether solution because it is sensitive for alcohol and water, and if it comes in contact with alcohol water it causes fire. Lithium aluminum hydride reduces a wide range of functional groups such as carboxylic group, ester, cyanide, amido group, epoxide, etc. So this is not very handy to use when we want to carry out reduction of aldehydes and ketones. In place of lithium aluminum hydride, sodium borohydride is very specific for the reduction of carbonyl compounds. It is a milder reducing agent, and it reduces only aldehyde and ketones, and it has no effect on other functional groups. So when we want to reduce aldehydes and ketones and some other groups are also present in the compound, then instead of lithium aluminum hydride we use sodium borohydride. Look at the example. Look at the example of reduction by hydride transfer. This is a compound which has carbonyl group and also ester group, and we want to reduce only the carbonyl group, only the ketonic group. So we use sodium borohydride, and in the second step hydrolysis. If we carry out this reduction with sodium borohydride, only the ketonic group get reduced, and we get a product which has this secondary alcohol in it, and this ketonic group get reduced to secondary alcohol, and this ester group is left untouched. Another example is a compound which has both nitro group and ketonic group, and we get a compound, a product where ketonic group is reduced to secondary alcohol, and this nitro group is unaffected. Sodium borohydride is also selective between carbonyl groups in different environment. For example, if we have a compound which has both conjugated and non-conjugated carbonyl group, then it is the non-conjugated carbonyl group which undergoes reduction. Let's see the example for this. This is the reactant which has a conjugated carbonyl group. This carbonyl group is a conjugated carbonyl group. It has this double bond in conjugation, and this one is non-conjugated carbonyl group. So here this non-conjugated carbonyl group, it undergoes reduction, and we get a secondary alcohol in the product, and this conjugated carbonyl group remains as it is in the product. In the same way, alpha beta unsaturated ketones on reduction with sodium borohydride gives 1,4 products instead of 1,2 product. This is alpha beta unsaturated ketones. When it undergoes reduction with sodium borohydride, it gives only 1,4 product, and 1,2 product is not formed. This is 1,4 product. Look here, this is first position, this O group is reduced to OH, and at this fourth position reduction occur and we get this 1,4 addition product. When reduction of alpha beta unsaturated ketones with borohydrate, sodium borohydrate is carried out in presence of catalytic amount of cerium chloride, then only 1,2 adduct is formed. This reduction is carried out in presence of cerium chloride. We get only the 1,2 product. Here reduction occurs at only first and second position, and we get 1,2 product in 100% yield, and 1,4 product is not formed. Another useful reaction which involves the combination of cerium chloride and sodium borohydride is the selective reduction of ketones in the presence of aldehyde. See, if we have a compound, the reactant, which has both the ketonic group and the aldehyde group, then ketonic group get reduced and aldehyde group is left untouched. This occurs when we use combination of cerium chloride and sodium borohydride. This combination discriminates between different ketonic and aldehydic carbonyl groups, affecting the selective reduction of the less reactive carbonyl group in a dicarbonyl compound. If we have two types of carbonyl groups in a compound, one is less reactive and the other one is more reactive, then reduction of less reactive carbonyl group takes place if we use cerium chloride and sodium borohydride as the reducing reagent. Let's take an example. If we reduce alpha beta unsaturated ketones, then the unsaturated ketones are reduced selectively in presence of saturated ketones. We have a compound which has both alpha beta unsaturated ketonic group and a saturated ketonic group. Then the less reactive alpha beta unsaturated ketonic group is reduced and the saturated ketones is left untouched, unreduced. This is an example of such a compound. This is the saturated ketonic group and this is the alpha beta unsaturated ketonic group. Here the more stable and the less reactive alpha beta unsaturated carbonyl group is reduced to secondary alcohol, and this carbonyl group is left as it is in the product. Similarly, ketonic groups are reduced selectively in the presence of aldehydic group, a compound which has both a ketonic group and an aldehyde group. Then the ketonic group is reduced. This is such an example. Here only ketonic group is reduced and this aldehydic group is left as it is in the product when we reduce the compound with cerium chloride and sodium borohydride. It is believed that under such reaction conditions, the more reactive aldehydic group is protected as the hydrate. It is first protected as the hydrate, which is stabilized by complexation with the cerium ion, and it is again regenerated at the end of the reaction when we isolate the product. This is how it happens. This compound is first hydrated. This compound, the aldehydic group, in this compound the aldehydic group is first protected by hydration. This is the hydration. This hydrated product is stabilized by complexation with cerium ion. Once this aldehydic group get protected, it is then reduced with sodium borohydride, and since this CHO group, this aldehydic group is protected, it does not undergo reduction. Only this unprotected CO group, ketonic group, is reduced and we get this compound, which on workup gives the product, final product, where the CHO group is as such and only the ketonic group is reduced to secondary alcohol. With ketones which contains now aldehydes and ketones can also be reduced with borane. This is another method of reduction of carbonyl compounds. Aldehydes and ketones are also reduced with boranes. Reduction of carbonyl groups by borane takes place by addition of the electron deficient borane to the oxygen atom. The first step is the addition of, this is borane BH3. It is electron deficient in nature. As we all know, it get attracted to the lone pair of electrons of carbonyl group and it get attached to the oxygen. This is how it happens. In the next step, the pi electron between pi bond between C and O get transferred to the oxygen, and this hydride ion is attached to this C plus of carbonyl. This is an irreversible transfer of hydride ion from boron to the carbon. This compound is formed. It is then hydrolyzed and we get the secondary alcohol. Under normal conditions, reduction of a pro-chiral ketone leads to racemic mixture of secondary alcohol. Now what is a pro-chiral ketone? Pro-chiral ketone हम उसे कहते हैं जिस कीटोन में एक कार्बन इस तरीके का होता है कि रिडक्शन के बाद, रिएक्शन के बाद वो एक कायरल कार्बन में कन्वर्ट हो सकता है. तो जब प्रो-कायरल कीटोन का रिडक्शन हम इन कंडीशंस में करते हैं बोरेन के साथ, तो जो प्रोडक्ट हमें मिलता है वो एक रेसिमिक मिक्सचर होता है सेकेंडरी अल्कोहल का. दिस इज़ द एग्जाम्पल फॉर दिस रिएक्शन. दिस इज़ अ प्रो-कायरल कार्बन which has 3 different groups. 2 of the valencies are attached to oxygen, and after reduction it is going to convert into a chiral carbon. So the secondary alcohol that we get after the reduction is a racemic mixture. In case of pro-chiral ketone, the major enantiomeric form can be predicted by Prelog's rule. प्रीलॉक्स रूल से हम ये प्रेडिक्ट कर सकते हैं कि जो रेसिमिक मिक्सचर बनेगा उसमें मेजर एनेंशियोमेरिक फॉर्म कौन सी होगी. ये रूल ये बताता है कि जो अटैकिंग रिएजेंट है वो कंपाउंड के उस फेस की तरफ से अटैक करता है जहाँ पे स्मॉलर ग्रुप अटैच्ड होता है कार्बन से. लुक, द कार्बन ऑफ कीटोन is attached to 2 different groups. One of the group is larger than the other group. So in case of pro-chiral ketones, the major enantioform can be predicted. According to this rule, if the steric difference between the large and the small groups attached to the carbonyl group is large enough, the reducing agent attacks from the less hindered face to give the corresponding alcohol. This is the smaller group and this one is the larger group. So the attacking reagent reacts from the side which is attached to the smaller group due to steric hindrance. So we get predominantly one of the enantiomeric form as the product. Another way of reducing aldehyde and ketones utilizing hydride ion transfer is from secondary alcohol. The reagent for this is aluminium isopropoxide, and the reduction is known as Melvin Ponderoff Virulay reduction. The reduction is carried out in isopropyl alcohol. This reaction takes place under very mild condition. This reaction is highly specific for aldehyde and ketone. This is the utility of this reaction. Here the hydride transfer occurs from a secondary alcohol. Earlier we have read about lithium aluminium hydride and sodium borohydride, and this is the third method in which the hydride ion transfer from a secondary alcohol to the carbonyl group. And the reagent for we used in this reaction is, in this kind of reduction, is aluminium isopropoxide. This reduction is very specific, and other groups which are susceptible to reduction, if they are present in compound, in the carbonyl compound, they are not reduced, and reduction occurs only at the carbonyl center. Let's see the examples. Here aluminium isopropoxide and secondary an isopropyl alcohol, a secondary alcohol, is used as the reagent. Two groups are present in this compound, CHO or Na2, and reduction occurs only at the aldehydic group. In the second example, reduction occurs at this CO only, and this cyanide group is not reduced under these conditions. In this compound also, alkene double bonds are also present, but these are not reduced, and only ketonic group is reduced to secondary alcohol. Here also this group is reduced to secondary alcohol. So this type of reduction, where hydride ion transfer occurs from secondary alcohol, is very specific for aldehydes and ketones, and this occurs in very milder conditions. Next, we are going to talk about reductive cleavage of a carbon-oxygen double bond. Earlier, in the hydride transfer reduction, CO, aldehyde and ketones, are converted to primary alcohols and secondary alcohols respectively. But in reductive cleavage of carbon-oxygen double bond, a CO group of aldehyde and ketones are converted to CH2 group, and this occurs through Wolff-Kishner reduction and Clemencian reduction. In Wolff-Kishner reduction, we heat the mixture of carbonyl compound, hydrazine hydrate and sodium or potassium hydroxide in a high boiling solvent such as diethylene glycol at 180 to 200 degrees centigrade for several hours. Then CO group converts to CH2. This reaction can occur in milder condition also, and excellent yields of the reduced product are obtained with sodium tertiary butoxide in DMSO. If we use, instead of diethyl glycol, if we use DMSO in presence of potassium tertiary butoxide, then reduction can often be carried out at room temperature. This reduction, there is a limiting condition for this reduction that you have to keep in mind while carrying out this reduction, and this is that this reduction cannot be used for those carbonyl compounds which have base sensitive group such as halo group and tosyl group present in the aliphatic system. Keep in mind, aliphatic system. So Wolff-Kishner reduction cannot be used for compounds, for carbonyl compounds which along with carbonyl groups have base sensitive groups. Let's look at the examples of Wolff-Kishner reduction. This is a compound which has CO group and it is converted to CH2 group. This is reductive cleavage of carbon-oxygen double bond. Oxygen is removed from this reaction and we are using hydrazine, potassium tertiary butoxide in DMSO. Here in the second example, this is aromatic halo compound. So this is not touched, this is not this remains untouched in the product, and only CO group is converted into CH2 group. Here we are using NH2 that is hydrazine and sodium hydroxide in a diethyl glycol which is a solvent. In next example, here halo group is attached to the aliphatic system, so it is removed and we get a double bond HBr from this compound is removed. because we are carrying out this reaction in basic medium, and this group is converted into CH2 group. These are another examples of Wolff-Kishner reduction. If Wolff-Kishner reduction, if alpha diketones are treated under such conditions, under Wolff-Kishner reduction conditions, then alkynes are formed. This is the diketone, and it is treated under Wolff-Kishner condition, that is with hydrogen, alcoholic KOH and glycol. Then it converts to alkyne. This is the mechanism of this reaction. In the first step, simple condensation reaction occurs between one of the CO group and hydrazine. H2O is removed and we get this addition product, Bonds are formed and bonds are broken in this compound. The double bond between C and N, one of the bond breaks and moves between C and C, carbon and carbon, and here H plus ion is removed, which goes to O minus here. In the next step also bonds are broken and we get an alkene, water and nitrogen as the product. Another way of converting CO into CH2 group is Clemencian reduction. In Clemencian reduction, carbonyl compound is refluxed with zinc mercury in presence of concentrated HCl. Here again, since the reaction medium is acidic, so we cannot carry out this reduction if some acid sensitive groups are present, along with the carbonyl group in the compound. This reduction is not applicable for acid sensitive compounds. So both Wolff-Kishner and Clemencian reductions are to be carried out keeping in mind the other groups which are present in the carbonyl compound. So we need a reagent which can be used for both acid sensitive as well as base sensitive compounds. Conversion of a carbonyl group to a thioacetal followed by hydrogenolysis is a way to convert CO into CH2 group. This reduction takes place under neutral conditions. Hence, CO group can be reduced to CH2 by this method in all types of compounds. So here we treat the reactant, that is a carbonyl compound which has some other group which may be acid sensitive or base sensitive. We treat this compound with thiols. When this compound is treated with thiol, a thioacetal is formed. Look here. This is a compound which has this carbonyl group and this ester group. This is first treated with thiol. This thiol attacks as the CO group and we get a thioacetal. This is a thioacetal. The thioacetal formed in such a way is made to undergo hydrogenolysis with hydrogen in presence of Re-nickel, and we get a compound which has CH2 group instead of CO group, and this is the reduction of CO. This is the reductive cleavage of CO group into CH2 group, and this reduction can be carried out with compounds which has such groups which are either acid sensitive or base sensitive. This is another example of this type of reduction. The next reduction we are going to talk about is enzymatic reduction. The ketonic carbonyl groups of beta ketoesters and cyclic ketones are also very conveniently reduced with high stereoselectivity by fermenting with baker's yeast. If we use baker's yeast to ferment beta ketoesters and cyclic ketones, then we get products, reduction products, which are very stereoselective in nature. Reduction of ethyl acetoacetate with baker's yeast give the S alcohol. On the other hand, reduction of ethyl beta keto valerate gives the R alcohol. These are the examples of reduction with baker's yeast. We get highly stereoselective products. The ketonic moiety in the side chain of cyclopentadiene could be selectively reduced to the R alcohol when we treat it with baker's yeast. This is the CO group in the side chain of cyclopentadiene, and it is stereoselectively reduced to OH and give R alcohol. Next is reduction of ketones into vicinal diols and alkene. Here we are talking about only reduction of ketonic groups, not the aldehydic groups. Ketones convert into pinecols when treated with magnesium mercury or aluminium mercury in presence of a protic solvent followed by hydrolysis, acidic hydrolysis. So ketones are first made to react with magnesium mercury or aluminium mercury in presence of some aprotic solvent, and this is in the next step it undergoes hydrolysis, acidic hydrolysis, and converted to pinecols. This reaction is known as pinecol reaction. Two molecules of ketones are treated under these conditions, and this is the product pinecol. This is a vicinal diol. Vicinal diol is a compound which has OH group on adjacent carbons. In pinecol reaction, ketones first convert into radical anions. Radical anion is an intermediate which has both the free carbon radical, and carbanion and anion group on it. This is ketyl radical. In this reaction, ketyl radical is the intermediate, and it is formed in the presence of magnesium or aluminium. This ketyl radical undergoes dimerization. The dimer on hydrolysis gives the product. These are the steps of these reactions. In the first step, homolytic fission of pi bond occurs between C and O on both the molecules of acetone or ketone. One electron from magnesium goes to both the oxygens, oxygen free radical here, and it converts into anion. This is the radical anion, carbon free radical and minus charge on oxygen. This is the intermediate which is attached, the minus oxygen, the oxygen anion is attached to magnesium here. Dimerization of these radicals occur at this position, and we get this product. This is then made to undergo acidic hydrolysis, and we get pinecol, vicinal diol. Aromatic aldehydes and ketones are also converted into pinecol by the use of titanium chloride, magnesium, and catechol. If we want to convert aromatic aldehyde and ketones into pinecol, then we have to use titanium chloride, magnesium, and catechol. This is the example of such a reaction, and we get this pinecol, aromatic pinecol. Pinecols are also obtained using titanium chloride in conjugation with zinc copper or lithium aluminum hydride. In this reaction, titanium metal is generated from titanium chloride in the presence of reducing agent. So if we use titanium chloride with zinc copper or lithium aluminum hydride, then in the first step titanium metal is generated from titanium chloride. The Pinecolor obtained in this case further reacts with titanium to give alkene. So the end product of this reaction is alkene. The conversion of ketone into alkene is known as Macmare reaction. So when we try to make Pinecolor using titanium chloride, zinc copper or lithium aluminum hydride, then the end product we get is alkene instead of Pinecolor, and this is the Macmare reaction. Let's look at the example. We are reducing this cyclic ketone with titanium chloride, zinc and copper. This is the Pinecolor that is formed. This reacts further with titanium metal from titanium chloride and converted it to alkene. This is another example, and we get trans alkene as the major product. This reaction works very well intramolecularly, and this reaction is very useful for the preparation of medium or large ring cycloalkenes. When we use this reaction with a long chain alkene, then intramolecularly this reaction takes place and big rings are formed. Big ring of cycloalkenes are formed as the product. This is an example of such kind of reduction, intramolecular reduction. This is all about reduction of aldehyde and ketone. Thank you.